Well, thank you for that introduction. Hello. Okay. So my name is Mikola. I work at Socket, and previously I wrote a whole bunch of JavaScript stuff all over the place over many years. So I did a bunch of work on Voxel.js and the Regal WebGL framework. I've also done a bunch of random blogging at 0fps, and I also wrote a bunch of the early numerical computing stuff in JavaScript. So like the ND array stuff in NPM is mostly my fault that is what it is. Right, so anyway, what I'm going to talk about today is like a little bit about what we do at Socket and kind of how it works and like some of the tricks that we had to do to actually make this like run at scale, right? And then, maybe kind of conclude with a few thoughts about what seems to be working right now, maybe where things are going in the future, and, like sort of like what are some kind of speculative ideas and trends that I see right now. So the first question is like, okay, malware, right? How bad is malware on NPM? Well, I mean, we use a lot of packages from NPM. I mean, a typical package might have, 79 or 80 dependencies. This is some older data that we collected from this study. Also, most application code that you're actually shipping or deploying in production is coming from open source packages and dependencies. So, we have about 90% of all the code that we're actually running isn't even code that we wrote. It's just random stuff that we downloaded from the internet without looking at it too carefully. And if even one of these things is bad, I mean, you're basically owned. So for example, the colors.js, attack, right, is still installed like 2.5 million times a week and used in about 29,000 public repositories, which is kind of insane, right? And also this stuff can kind of sit around for a while. It's sort of sneaky. So sometimes these malicious packages, they get on the registry. They'll sit around for almost like half a year or more. And a lot of them will hang on sometimes for more than a year. And this is not great, right? They're just sitting there as like a little booby trap for someone to install them and then get completely hacked by some bad piece of code, right? That could steal all your environment variables or root your computer, hack your production environment. Generally not good stuff. So like, how do these things happen? How does this malicious software get out there? So there's sort of two general patterns that happen for malicious software. One is either a maintainer will become compromised, so a legitimate package becomes hacked, or an attacker will publish a fake package, basically. So how do packages get hijacked? Well, one is you could just use a weak password, like, oops, I set my password to test123, and there we go. Or maybe, maintainer gets like burned out and accidentally gives a bunch of access to someone they shouldn't, like in this like XZ backdoor example. Or maybe the maintainer just, goes AWOL and forget to take their meds or something, and then they become a malicious actor. Or, they just like, that can happen, right? Or maybe, the maintainer becomes, convinced that there's a political cause they want to support, like war in Ukraine. They oppose that, and they put some messages inside their packages, which, I mean, you might agree with their general sentiment, but maybe you also don't want to trash your production deployment, in the name of something like that. Or maybe, your laptop as a maintainer gets infected by malware because you install a malicious dependency or something. And so now they're compromised and all of their things would happen. Or you update one of your dependencies to a malicious dependency, or you just get, sort of coerced by a government into doing something, right? Like maybe, that you're working in some foreign country and then they decide to pull you aside or something like that, right? So all these things can happen, right? And things like, signing or checking, authenticity of packages is not sufficient to ensure that the contents of the packages you're actually installing are safe to run. So, and like these are legitimate things that we have seen happen that are going on today at a large scale. There's also typo squats. So we're actually right now in the middle of like some ongoing typo squat campaign. There's currently some malicious actor that's been flooding the NPM registry with hundreds of fake packages with names like Muskie instead of Husky or whatever, trying to trick people into installing them, or Next with 2 E's, right, instead of Next, that sort of thing. So, examples of typo squats could be like Lodash versus Ludash, or things like this. And so if you, accidentally make a mistake when you're typing in the name of the package and you install the wrong one, then you get malicious code and you're hacked. Similarly, if you happen to be using a private NPM registry and someone figures out that, there is maybe a mirror of that package, or like that name is not claimed on the public NPM registry, they can just go in, grab that out from under you, and then if someone tries to install the package without using your local registry proxy, they will install the hacked version and then you're owned. So this has happened at several major companies in the United States, and is another common vector for getting malicious code into developers' machines. I mean, also people can impersonate popular package authors. So, for example, I don't know if you can tell the difference between Cindersaurus and Cindersrohus, right? But apparently the latter is like, really into crypto and has a, nice like little Ethereum wallet that you can send a donation to by installing one of their packages, right? Or you could also just typo squat CLI operations too, like save dev and then save dev, install the wrong dependency, and that's it. So there's lots of ways you can end up installing malicious code through, just either an accident or, like a mistake, or even just through some legitimate package being compromised. And once these malicious pieces of software get onto a developer machine, your whole company could become completely owned, because then they would have access to all of those credentials, maybe public, or maybe your private infrastructure, or whatever. So this is generally not good, right? So what can we do about this, and how do we stop this? So maybe AI can do it, and well, yeah, I mean, this is kind of how we approach it, and this is our sort of idea. We, try to use AI to detect these malicious packages and typo squats, and also, identify other, implants and packages that might be a little sketchy, like telemetry, like surveillance, logging stuff that people insert into their packages. Also just looking for general anomalies or, suspicious patterns within packages or potential vulnerabilities. And we can also use this to do things like generate package recommendations. And we have plans for future applications of this for things like CVEs and license scanning improvements too. So there's a lot of potential applications here. So does it work? Well, here's an example of some malware that we've caught, using ChatGPT. Hard to tell what it's doing like off the top, just by looking at the code, but ChatGPT is fairly confident that it's malicious, and they're correct. It was actually malware. Another example of a malicious piece of software caught by, ChatGPT. You can just throw it into the AI scanner, and it will tell you that, this is basically stealing your environment variables, or here's an install script that basically, like sends all of your information to some remote host and steals all your credentials. And then this is literally, I just went into our internal dashboard and took a picture of what we caught this morning. So if you look, the timestamp here, it starts at 6:55 a.m. and ends at 7:40 a.m. This is just a random sample from when I took the screenshot. And you can see we got about, I don't know, like 8 new packages here that are all obviously malware. So we have one that, steals system data, another one that downloads and executes some random file from a remote host on your computer maliciously, etc., right? So great, these can find malware, but the main challenge is this would cost a lot of money if you just did it by brute force. So if you literally just took the whole NPM registry and stuffed it into ChatGPT, you're looking, even if you do it like the cheapest possible way using the batch API at $1.25 per million tokens, back of the envelope, that's probably not going to work, right? So you can't just throw AI at the problem, because even though the AI is pretty good at catching malicious software and distinguishing between, like a benign use, for example, of some API or a malicious use, it's not easy to just throw everything into like the AI system and get a result out, right? Or at least at this point. So how do we get around this, and what do we do? So the trick that we use is we have sort of a stack of filters approach to basically running these AI systems at a large scale. So we have sort of a feed of the NPM registry that we tail, and we get updates from new packages as they're published. And then these go through some static analysis process where we look for potential signals. And these are generally noisy in the sense that we're going to get a lot of false positives at this point. So we want to basically just rule out the things that we're fairly confident are not malicious because they don't access anything that could potentially be used for a malicious purpose. So we look for like API access or obfuscated code at this stage. And then if we find something that's maybe suspicious, we first do a pass using a fairly cheap LLM, which is, again, quite noisy, but we can use this to just reject fairly benign uses of these behaviors. And then if we have something that actually looks like it might be potentially bad, then we can send it into a much more expensive AI system. And then those then go into a queue where we can then triage them using human review. Or if you're feeling lazy because there's a lot of work, we can then send it to an even bigger AI system that costs even more money, and that will then automatically annotate them. Then also, for our typo squats here, we have a separate system for handling typo squats, which is, again, mostly AI-driven. So I'll come back to that in a moment. So how does the static analysis work? Well, basically, like the whole goal of the static analysis is to just eliminate obviously safe packages from this feed of packages that we're looking at. So if we have a package that comes in, we want to get rid of it. And already as part of Socket, we have like 70 out of the box, like different alerts that we detect. And we also have a variety of additional signals that we check internally. And these work okay, but they're extremely noisy. So there's generally a large amount of packages that will get through here. So this is basically killing like maybe 70%, but there's still like 30% of the packages will get through, or some large fraction will go through. So only the packages, though, that have some sufficiently risky prior signal that they are potentially dangerous will then go through to the actual AI scanning. And so this is like where we basically get a big chunk of cost savings here is by just discarding the stuff that's obviously not malicious. The other thing that we also do is we cache and memoize all of these results that we compute, like as we go incrementally. So, and we do this, at sort of both the package level, but then also with the finer granularity within the file, within each package. So both at the file level and the prompt level. We generally want to avoid like repeating work by running the same AI prompt twice because that costs a lot of money, right? So we try to save everything as much as we can as possible. And as a side note, this is another advantage of running a system for this sort of like moderation in a centralized way because it allows us to amortize the cost of doing these AI scans over all of the users of Socket. So if you're using Socket today, you don't have to then pay all this money and set up all this infrastructure to do the AI scanning. You can basically get it for much cheaper by getting it through Socket. So it's like an AI buyer's club, basically. So that's another way that this sort of makes a little more sense to do this. So the sort of two cost savings are we basically try to reduce the amount of work that we do, and then we try to basically distribute the costs over many users. So if everyone's going to be checking this package, we only have to check it once rather than everyone bringing their own API keys and checking it a separate time, which would be very wasteful, right? So if everyone's scanning the same code over and over, not a good thing to do. So yeah, and then a little bit about how we do our prompting. I mean, we use the standard best practices with chain of thought prompting, which is the sort of simple idea where you just ask the AI model to think a little bit before it gives an answer. And this, asking the AI to sort of like first look for interesting features, then think about the code, and then come to a conclusion, generally makes these AIs like produce better results, and they think a little bit more clearly than if they just have to, off the cuff, come up with an answer immediately. But this is also very contingent on the order that you output your results. So again, we also have to make these AIs output some structured JSON that we can then interpret and then store in our system. So we have to make sure that like one important thing to remember when you're building these prompts is you want to set it up so that the chain of thought reasoning happens at the very first part of your prompt output, and then the thing you're looking at comes out afterward. Otherwise, what will happen is because these things just generate text one token at a time, if you have them output the decision first, then they're just going to generate some post hoc reasoning rather than thinking first and then using the reasoning to make a choice, right? Instead, they'll basically say something and then reason afterward to justify why they just said what they did, which is not what you want. You don't want them to do that. You want them to think a little bit before they give an answer, which is, intuitive, I guess, because humans, I think, work in sort of the same way, but it's also a little weird, from a kind of programming perspective, that's not how normal programs generally work. And another important thing that we also do, too, is we actually run all of our prompts multiple times. And the reason for this is that we try to get a sample of different possible interpretations. So for us, we don't want to have too many false negatives. So we would like the AI we would like to basically sample different possible interpretations of what some artifact is before we try to pick one as the main de facto choice. So we try to generate different possible completions that are as diverse as possible to sort of cover all of our bases, right? So in the early stages of our prompting here, you can see that we first do the static analysis. If we catch it, then we run this cheap LLM, and then we'll basically have it generate many completions of the same prompt that are all different. So we have it sort of generate a tree of possible choices. And then if all of these choices show that there is no detectable signal for malicious code, we can, with fairly high confidence, say that this is a fairly safe package and then just put it into our approved package feed. Whereas if there's any inconsistency or doubt or uncertainty across all of these models, then we can move it to an actual smarter LLM. And then this can then go into our triage feed, where if it's high suspicion, it'll be instantly blocked. Medium things go for human review, and then low suspicion packages are default approved. And so we also still have to use human moderation at the end of the day to review all of these things because, first of all, the AI systems can still make mistakes and there can still be false positives, and we don't want to waste users' time with that. But also, it's important to observe what's going on in these systems to measure the performance of these models and make further improvements to the training. And then finally, we also have implemented some more expensive AI agents on top of these that can also be dispatched to do a deeper analysis. So for example, if we have a highly obfuscated package, we can run this through a much more expensive AI system that can then pull apart the files and figure out exactly what's going on inside that. So this agent-based system was only recently possible because these more expensive models like O1, which is pretty much the only reasoning model available today, are able to do these extended chains of sequential reasoning. So the way I sort of intuitively think about O1 is it's sort of like GPT 4.0, but without the need to do any prompt engineering at all. You just ask it what you want it to do, and then it just works out of the box. You don't have to tweak what you're asking it. It just will automatically generate all of the chain of thought prompting on its own. However, this is unfortunately really expensive, so it's maybe a couple of bucks to scan a package using O1. And there's very restrictive API rate limits at the moment. And in some cases, it's actually just cheaper to triage these things with a human reviewer. There's, the AI system costs more than just doing it by hand. But on the other hand, because it can work pretty quickly, and it can also attack a lot of the more difficult pieces of malware out there to get more of a precise interpretation of what the code is doing, it can still be useful to have this, but we require a human to initiate these scans. And so that's basically how the malware scanning works inside Socket. So now I want to say also a few words about how we do typo squat detection. So in the initial versions of our typo squat detection, we used Levenstein distance and some static rules and hacks to try to identify typo squats. And we were able to get this to kind of work, but it was pretty fragile, and we had a lot of noise, right? So there would be many potential false positives, and when people see a false positive for a typo squat, that's a terrible user experience. We also found that as we started to expand to support more ecosystems like Maven and Golang, it wasn't very effective. So basically, Maven package names are really, really, really long, and so looking for Levenstein distance typo squats is not necessarily a great way to identify all of the potential ways that you can mistype a Maven package name. And same for Golang because they're just URLs, right? So you could, squat a domain or whatever. And it doesn't necessarily work. So one thing we did somewhat early on to eliminate some of the false positives was we did add a second LLM pass to triage typo squats. So we would first generate potential typo squats, and then to eliminate false positives, we'd feed them into, like some fancy LLM model to have it evaluate whether these typo squats are real or not. And this worked fairly well to eliminate false positives, but it didn't fix the underlying problem, which was that the Levenshtein distance would sometimes give us false negatives in some of these very verbose ecosystems. So since then, we've actually moved away from these text-based or like string-based typo squat detection approaches, and we now use vector embeddings to determine semantically similar package names. So the way we resolve typo squats right now is we take the package names for all of these things and we just stuff them into a big neural network. It spits out a vector, and then we can just find any packages that are close to that vector. And if there's a popular package that happens to be semantically similar, we can flag it as a typo squat. And this works great. It's a much simpler approach from a sort of like programming perspective to deploy and implement this, although it's, now we have to like run more AI stuff, which becomes operationally challenging. So that's basically it. That's the high-level view of how we do all of our AI scanning and detection. So I guess some final thoughts here. So first is, does this work, and like, is it effective? So I would say initially, like, no security tool does catch everything, but this is a huge improvement over most code scanning tools. So the problem with many SaaS tools is that they're simply way too noisy, especially to be using them on dependencies. So many companies that use SaaS tools will run them on their own internal code base, and then they can manually triage every alert that comes through something like CodeQL or SemGrep or whatever. But if you try to run these on open source packages, then the noise level from these SaaS tools is just off the charts, and it's completely useless for detecting anything. So the AI tools that we built have significantly lower noise, right? So much fewer alerts per package than like a naive, brute force SaaS approach. Also, I mean, things like CVEs aren't really designed to catch malware. There are things like the OSV malware database, but these tend to be very slow and reactive, and they're not able to catch like new malware campaigns in real time. So many of these packages are flooding these registries constantly, and if you happen to get hit by one of them, then you're just done. So they're not fast enough to basically catch the malware as it's getting yanked out of NPM or PyPI or wherever. So in practice, I mean, we catch hundreds of these malware packages every week, usually within seconds of them getting published, and this allows us to auto-block definitely bad packages nearly instantly. And also, though we didn't set out to do this, this actually does catch some level of vulnerabilities as well as an accidental side effect. So it is somewhat useful for catching CVDs. So although we report them as merely potential vulnerabilities, we don't try to triage them or push them through the CVE databases at scale with this. We also found a few things that didn't work very well. So one approach that seems very popular right now in a lot of AI space are retrieval augmented generation, or RAG-based document searches. We did not see much benefit from trying out any of these RAG approaches. So we do not use any retrieval augmented generation in any of our AI tools. Also, a lot of the agent frameworks that exist, like LangChain, we don't use any of that stuff. It's like the prompts tend to be pretty simple and fairly self-contained. So the actual amount of code involved in setting up and spinning this is not that significant. So it's pretty easy to deploy that part of it. It's more the bigger issue is more the optimizations around cost reduction rather than so much the prompting itself. So those things have not turned out to be very interesting. It is the case, though, that many of these base models are becoming a lot smarter, and so in the future, probably agent-based operations will start to become more interesting, especially with the new Claude computer use capabilities or O1's longer reasoning capabilities as well. So some general kind of speculation about this. Just sort of looking at where things are going and how these context windows are getting bigger, and these models are now kind of coming out of the box with some pre-built reasoning or automatic chain of thought fine-tuning built into them. It seems like the amount of work involved in prompt engineering is going down. So it's getting a lot easier to get these things to do what you want them to do and do it correctly. So you don't have to set up as much extra infrastructure. So I think a lot of these extra wrappers or things are probably going to just disappear, or like they're going to become less useful. Also, the costs have come down a lot. So last year, if I were to give this talk, it would have been about $1 billion to scan the entire NPM registry, and now it's merely 50 million, which is a significant cost reduction in about, in a fairly short amount of time. So it's possible that, maybe at some point in the future, we may just be able to completely brute force scanning the entire registry of every package that's ever been published, right? So $50 million is starting to seem like you could do it with enough money. I'm not sure, you necessarily want to do it today with the current models, right? Because, maybe something better comes along and then you'll have to redo that again, so another 50 million, but could be feasible in the near future. And also, I've observed that a lot of the models seem to be converging to very similar levels of performance, which is sort of like around GPT-4 type stuff. The closed models still have an edge, especially Claude 3.5 and o1, although the very best closed models tend to cost significantly more than the open models. The open models like the Llama 405 and whatever are cheaper, but they're not as good. So, you have to pick when you deploy them strategically. It doesn't make sense to use those models for tasks where high accuracy is extremely important yet. But because they are kind of converging, I don't know. It feels like maybe there is a data wall with this. I don't want to say that too out loud. I'm not an AI insider, but it remains to be seen if maybe we see another big jump in capabilities with the next generation of models. But it could also be that maybe we do plateau, but the costs continue to go down. And if that's the case, there's still a lot of interesting applications and low-hanging fruit for AI, and especially in cybersecurity, both offensively and defensively. So I think probably at Socket, we're going to continue to extend and support more ecosystems and probably improve the accuracy and performance of our LLM analysis, and probably add more AI features to our product because there's a lot of potential applications for this. So that's about it. So here's some acknowledgments. So I'd like to thank Philip, who is basically currently running a lot of our threat analysis and review. Firas, the founder of Socket, and also the Socket threat analysis team and the rest of the developers there. And NodeConf.eu, because you guys are great. So that's it. So thank you. Please stay secure.
So thank you so much for that, Mikola. It was really interesting. I'm sure somebody's got some questions here. Oh, I knew it. Hello, Patty.
Thanks. That was a really interesting and great presentation. I have a couple of questions. First of all, what's the rate that you find with false negatives? Mm-hmm. And the second would be more about prompting. So how do you handle, I'm very curious on knowing, how do you handle the version control of the prompts that you use? And do you have some kind of prompt library where you store all the prompts depending on where you use them, and have kind of that version control?
Yeah, we just write all of our code in TypeScript, and our prompts are basically defined in line in the same TypeScript files where we call the underlying AI model. So it's all just version controlled in Git. Was there another question, or is that okay? Or,
no, it makes sense.
Yeah.
It's just that is some teams they like to have the prompt library apart from the repositories of code. And the other one was the rate of false negatives.
Yeah, false negatives are kind of unknowable, right? Because you would have to know when you miss them. So at the moment, it's like we can't exhaustively check every single package by hand. So this is sort of philosophically at this point indeterminate. I don't actually have a good way to do that. If you have a good idea how we could even calculate this at the moment, I would be very open to it. But if we had a baseline truth value, we'd probably just make that our product and do that instead. So the short answer is, I don't know, it seems good, but I don't know how to do it. I really have no way to answer that question.
Any other? Oh, there's loads of questions, right?
Have you done any experimentation with trying to just reduce the amount of data that you're sending to LLMs? Like maybe if it's a new version of a package you've scanned before, only send the diff of what's changed, or if there are certain files that you think are low risk because they don't import any network stuff or import any environment variable stuff, maybe don't bother sending the code from those files.
Yeah, that's basically what we do. So we do not send we try to sort of filter out exactly the data that needs to go into the underlying LLM when we do a scan for it. But because these things are essentially stateless, you have to copy all of the relevant information into the prompt in order for the model to give you some reasonable assessment of the risk of whatever file it is you're looking at. So, yeah.
Cool. I really enjoyed the talk. Thanks. I understand the need for a tiered strategy because of what you mentioned about the pricing constraints on the bigger LLM models, but I guess that means for the adversary, they only need to overcome the initial cheaper model in order to get that fast path to a green check.
Yeah, that's correct. I would actually say that currently that cheaper model is the weakest part of our current approach. But the good news is that will probably go away as the cost of these things goes down. So eventually, maybe this whole thing gets a lot simpler and we can just run it directly through the fancier model. So, and I think looking at trends, that's probably where things are going to be going in the future.
Okay, hey. Full disclosure, watching the malware feed from Socket is kind of my hobby. I do that late at night when I can't fall asleep, and I still want to do something other than watching YouTube mindlessly. But my question is, the vast majority of detections are first-time published packages, often by security researchers disregarding NPM terms of service. Do you differentiate new packages versus existing packages for scanning, and do you pay more attention to packages that have larger adoption?
Well, we try to just scan all of them, so we try to treat them equally. A package comes in, and then we just try to go through it and scan it as best as we can with the resources available to us. So we look at them all, basically. We check all the code of all the packages.
Yeah. Do you have a team? Do you have a team that try to circumvent your detection? Inside, do you play cat and mouse?
Yeah, I mean, we do, of course, try to break it and red team it and, fix things that pop up too. And if we miss something, we go back and we do postmortems on that and try to make improvements. So, yeah.
Okay.